Let's go learn some chemistry so you can make that 5. What will it take me to maintain your drive? Hello, AP Chemists. So we've already talked about how to find a rate law using initial rate data, where you're given multiple experiments, their initial rates and the initial concentrations, and you're able to find a rate law using that data. That's great. But there's a lot of times when we're talking about rate that we also want to think about the relationship between a concentration of a reactant and time. When we are given times and concentrations, at that point we actually are talking about using the integrated rate law. Okay, so we're going to use the integrated rate law, which for some of y'all know that that's calculus. The calculus has already been done for us, and we're going to take that rate law and use it. Okay, there are 3 integrated rate laws that you are going to be responsible for, and I'm going to talk about all 3 of them in this video. The first is the first order integrated rate law. And so we can already kind of think that when we think of a first order reaction, remember that we have rate is equal to K, which is our rate constant, times the concentration of whatever we have to the first power. And of course, I don't have to include that 1. I'm just showing that to you. Okay, so if I know that a reaction is first order, because maybe I was told in the problem, or maybe I gave you a rate law, like I have right here, where we show that to the first power there, then I can use this equation right here, which is the first order integrated rate law, in order to calculate either what concentration we would expect to have at a certain time, or at what time would I expect to have a certain concentration. Okay, so just to kind of point out what everything is here, okay, this is my initial concentration. Okay, this is my concentration at time t, so just whatever time it is. T is time, and then we already know that K is our rate constant. Okay, and so we can just plug in the values that we need to solve for what is missing. Okay, now with that being said, I have concentrations here. You can also see this be absorbance values. So since there is a direct relationship between concentration and absorbance, we can just interchange those in the formula. Okay, big important point to make here is I can rearrange this equation to be in the form of y equals mx plus b. And so what ends up happening is when I plot the natural log of A versus time, so the natural log of A versus time, and I have a straight line, okay, so straight line, then I know that it is a first order reaction. Natural log of A has to be on the y-axis, time has to be on the x-axis for that to be the case. Okay, so if I were to look at these 3 graphs right here and ask you what the order of the reaction is, it's actually pretty easy. You would just tell me that since when I plot the natural log of A versus time, since the line that is produced straight, we produce a straight line when we plot that, we know that this is a first order reaction. So because this axis is natural log, this axis is time, and we have a straight line, I know that this is a first order reaction. So since we're talking about the reactant being A, I could write this rate law as rate is equal to K times the concentration of A. Okay, so here I have an example. It says that at 400 degrees Celsius, the first order conversion of cyclopropane into propylene with a rate constant of 1.16 times 10 to the negative 6 per second. If the initial concentration of cyclopropane is 1 times 10 to the negative 2 molar at 400 degrees Celsius, what will be the concentration after 24 hours? Okay, so we got to kind of think about what all we have. Okay, so I have this value right here. That represents my rate constant, or my K. Says the initial concentration of cyclopropane is this right here. So this is A at time 0 seconds. And then it says, what will its concentration be after 24 hours? So that right there is representing my time. One thing that I want you to be very, very cautious of, and this is the case anytime that we have a calculation, is that you are being very careful about your units, okay? Since this is in hours and this is in per seconds, we're gonna have to do a conversion to make sure that it's going to cancel out. Okay, so I'm gonna use this calculator, or this formula here. Okay, so this is the formula that we have available to us on the AP test. So it's not something that you have to have memorized. Okay, so I'm gonna just write it out here so you can see where I am plugging everything in. Negative KT. Okay, so like I said, our concentration at time T is what we are trying to find. So I don't have that information. My initial concentration is 1 times 10 to the negative 2nd power. K is 1.16 times 10 to the negative 6th power, and it's per second. So since that's in per seconds, I'm going to convert that 24 hours. I'm going to just do it down here. 2 seconds. Okay, remember that 1 hour is 3,600 seconds. You could just do 60 times 60, because that's how many minutes are in 60 minutes in an hour, 60 seconds in a minute. And that's where I got that number from. So that's 24 times 3,600, and I got that's 86,400 seconds that are going to be in 24 hours or in a day. So that's what I'm going to plug in here. And then from there, you'll notice that seconds are going to cancel, which is the whole reason we needed to make sure to do that. So I'm going to multiply those. So it's negative 1.16 times 10 to the negative 6 times 86,400. And I'm going to go ahead and rearrange this as well. And I'm going to add this over to the other side. So this is just doing the algebra, not showing every step completely. But I'm going to do that. To that, I'm going to add the natural log, which is a button on your calculator. It's LN. It's right below the button that says log. Okay, and I got that it's equal to negative 4.705. Okay, now we're trying to find the concentration of A. So those of you who are in pre-calculus should already be able to do this. And those that are in Algebra 2, you may be there, you may not. Okay, but to calculate what's inside, or to find what's inside of a natural log, I have to use E. Okay, so what I'm going to do is I'm going to do E, that, E of that, and then that's going to end up giving me the concentration of A at time T of 9.05 times 10 to the negative 3rd molar. Okay, so after a day, that would be my concentration of A. So that's how we're going to use this. That's going to be very typical of how we're going to do it for 0 order and 2nd order as well. The only thing is different is that the formula we use is just different. Okay, but that is how I would find that. Okay, There are questions on the AP test that deal with half-life as well. The only time that we're going to deal with half-life in AP is if it is a first-order reaction. We're not going to deal with zero-order or second-order reactions. Those get a lot more complicated, okay? So first I'm going to start with the definition. The half-life is the time required for the concentration of a reactant to reduce to half of its initial concentration. So if I have 1 molar concentration and it takes an hour to get to 0.5 molar, then its half-life would be 1 hour. So it's how much does it take to be halved. So in that case, I said that, okay, if that was 1 hour, then the half-life would be 1 hour. Okay, and then I would expect that after another hour, so after 2 hours have passed, it would have halved again. Okay, and that just kind of keeps going, and every hour or every half-life it would be halved in concentration again. Okay, one of the big important things, and you can see here that I put it in all caps, is that for a first order reaction, a half-life is going to remain constant, meaning that after it is halved, okay, it's going to take the exact amount of time, that same amount of time, to be halved again. So you'll see that the half-life is staying at 1 hour. That is not true for a zero-order reaction and not true for a second-order reaction. So that's something that you definitely want to look at. So I told you that graphically we can look at the y-axis and the x-axis to tell what reaction it is when there's a straight line. But you'll notice that in this graph that I have here, there is actually not a straight line. But you'll also notice that the mass, or the amount that you have, is halved. You can see here we're going from 10, then down here we have 5, 2.5, 1.25. But what you'll see is that the half-life is actually the same every time that it's halved. So what that means is, since we have a constant half-life, we know that this is a first-order reaction. Now, there are calculations for half-lives, and they actually come from the formula we were looking at earlier. Okay, but I can also use this formula. That's kind of ugly, but that formula right here. Okay, so where K is my rate constant and T sub 1/2 is the half-life. Okay, so we can just plug in our rate constant for a first order reaction only and calculate our half-life, or calculate our K or our half-life either way. Okay, so here we have that the decomposition of SO2Cl and Cl2 is a first order reaction with that K to determine the half-life of this reaction. So we're just going to use that formula. So I'm going to say 0.693 divided by 2.2 times 10 to the negative 5th per second. Okay, and I got 31,500 seconds. So the concentration would be halved every 31,500 seconds. Okay, here's another example. I think this one might be a little bit more complicated. It tells us the initial concentration is 1 molar. It says after 3 hours, the concentration has decreased to 1.2 times 10 to the negative third. What is the half-life of N2O5 expressed in minutes at 45 degrees Celsius? And so this one is a little bit more complicated because we can't just use that formula that was given to us, but we can use the first order integrated rate law. Okay, so, sorry. So we can use this formula. So we have the time, the concentration at time t. It went down to 1.21 times 10 to the negative third. We have the initial concentration, which was 1. We don't know the rate constant. We know that the time that passed is 3 hours. Okay, so at that point, I'm going to solve for K. So I'm going to plug this into my calculator. and I got that K is 2.24, and then that's going to be per hour. Okay, so that is going to be per hour. Now that I have that, I can figure out my half-life, which is 0.310 hours. Okay, well, and it asks for minutes. Okay, so that's 18.6 minutes. Okay, so that's a more difficult type of question, but one that you could actually have as well. So here's an advanced half-life problem. I'm going to look at this in class, but I think that trying it out yourself and seeing if you can do it would be a good thing to do. So go ahead and work that problem and bring it to class, and we'll take a look at it. Okay, so the last part of this is I just spent a ton of time on first order integrated rate law, and I'm honestly going to barely look at second order and zero order. And it's not that these don't show up, because they do. It's just that the process is very similar. Okay, so one thing that you will notice that's different is that when we have a second order reaction, that we are going to use a different formula for that. And so we see that here. We see that we have reciprocals here instead of natural logs, but you'll still see that it's time t minus time at 0. And then you'll notice that there's not a negative sign here as well. So it's just some like minor differences to look at. Just like we had for a first order integrated rate law, we can tell things graphically here. When reciprocal of concentration is plotted versus time and we have a straight line, then we know that it is a second order reaction. Okay, so that is what we are looking at there. For a zero order reaction, so here you'll notice that concentration does not affect the rate because it is zero order. This is the formula that we are going to use. All three of these formulas are found in your AP reference materials, and so you have them available to you on the test in here and also on the test that you have, or on the AP test in May. And so you'll notice once again, it's time minus time 0, and then on the other side we have negative KT just like we had for first order. The difference is the natural logs aren't there. So you can kind of start to see this pattern here, and you'll see right here that when we put the concentration of A versus time and we end up with a straight line, that is a zero order reaction. So just kind of summarizing all of that is this nice little chart here. So we have a differential rate law, which we talked about a little bit last class. Here we have what it would look like when we're looking at concentration versus time. Notice that for zero order, when it's concentration versus time, we have a straight, oh, that is not very straight, but we have this straight line here, okay? Then I have all three of the integrated rate laws. They've kind of been rearranged to look a little bit different, but those are all basically the same thing, just algebraically rearranged. We know that we can use what's on the y-axis and when we're given a straight line to determine the rate law. So you'll notice that when it's concentration versus time and it gives us a straight line, it's zero order. When we have a straight line and we have natural log versus time, then it's first order. And then if it's a straight line with a positive slope, and we have the reciprocal of concentration versus time, it is second order. So I always remember that as CLR, okay, where concentration, natural log, and reciprocal. Okay, so it is clear. Okay, that's pretty much, like I said, the only half-life you need to actually know is this one. The other one gets a little bit more complicated because concentration does play an effect on the half-life, but for a first-order reaction, since it is constant, that is not the case. Okay, and so you can go through and you can fill this out for other summaries as well. I might look at it in class too, but I think that looking at that might help you just kind of look at all the information I've just talked about and review it before you come into class. So in class, we will talk about all of this. I'll review it real quick, and then we will do some practice with integrated rate laws, look at some AP type questions, and also just some very good practice on that. All right, bye y'all. You are promising hardworking kids, and together we'll get through. This year I'll make a 5 out of you.